Good morning.
Today we are going to do a review of Chapter 8 and probably get through a little bit of new material on Chapter 8 if you took it this summer. If you took it in the spring semester, it'll probably just be all a review. I'm going to talk a little bit through the syllabus, and then we will get started for the day. So a couple of changes, things I noticed today. So I updated, these were set from 9 to 11. They're just the normal class hours, so 9:15 to 10:50. I'm going to send out or post a PDF for you guys. You guys will print it out, take it, scan it, and upload it. Or not scan it. Recitations. I had this listed as Monday, Wednesday, Thursday. It's Monday, Wednesday, Friday. Sorry about that. Most of this is fine. Probably way too much information on here. This exam or course breakdown, the points possible section, don't use that. Use the percentage section. The Wiley Plus homework won't let me break them into 25 points because there's more questions than that. So your Wiley Plus will be worth 20% of your grade, even though it'll be more than 100 points. So Wiley Plus will be 20%, recitation quizzes will be 20%, exams will be 60%, but this points possible section won't actually add up to 500. Let's see, grading scale. Okay, I think that's probably about everything I want to talk through for the syllabus. Let's see, I'm going to get out of here and switch over to my iPad. So, as I mentioned today, we're going to be talking about Chapter 8. We're going to start off by talking about some nomenclature. So, our typical nomenclature when we're dealing with carbon skeletons, say we have a 4-carbon skeleton. Oh, sorry. Yeah, there's a question in the chat, which is, it mentions that attendance for lecture and recitation will be monitored for a grade. So I'm not actually going to do the grading for attendance this semester. That was a Chem 255 thing that just got pulled over. I'll delete that from the syllabus. For the recitation, it's basically if you're there, then you have taken the quiz, because the quizzes are taken in recitation. So that'll be how we're like monitoring if you're there. But for the most part, I'm not actually going to monitor it. Sorry about that. A couple things that are still bugs we're working out today. So, Chapter 8, talking about nomenclature. Typically, if we had a 4-carbon skeleton, something like this here, we would label this as butane. When we add a double bond to it, and you notice this ends with ANE. When we switch to a double bond, this is going to go from being butane to butene with an ENE. Similar to thinking that this is an alkane versus an alkene. If we want to signify what position this is on, so if we were counting our carbons, this one's symmetrical, doesn't really matter that much. Our double bond is starting on position 2, so we would label this as a 2-butene. And that gets us half of the structure naming. So if you were to have someone tell you to write 2-butene, there would be two different options. You could either write this, or the other possibility would be to write out this here. So either a trans bond or a cis bond. Or you could also call it an E bond or a Z bond. So cis and trans really only apply to when you only have two substituents. If you have more than that, for instance, this here, now we have to start using E and Z nomenclature. So let's talk about what E and Z are. I'm going to delete some of this. Easiest way to think about it is that E is going to be trans, and Z is going to be cis. So for this molecule up top, you would consider this to be a trans configuration. So this would be a 2E 2-butene, or an E 2-butene. There's only one stereocenter. You don't necessarily need to write it out. It's a little bit redundant. Let's talk about a more complicated one, though. So let's say we had something like this here. So for determining E versus Z, what we're going to do is we're going to break it in half down our double bond. And then we're going to use basically just our R and S priority naming. So if we were to take a look at this, based on the naming you use from R and S, or the numbering used from R and S, you would say that this top ethyl group is a higher priority than this CH3 here. We can do the same thing on the other side. We would say that this ethyl here is a higher priority than this hydrogen. Because our two high priorities are on the same side, you would think of this like if you were to just kind of outline the two high priority pathways, it makes a cis structure. So we would say that this is Z. Alternatively, I'm going to do another example. Let's take a more complicated one. Like this here. We're again going to break it in half. Doing our priority naming on the left, we would say that fluorine is a higher priority than this CH3. Same thing on the right, we would say that this carbonyl on top is a higher priority than isopropyl. Our highest priorities are on opposite sides of our double bond, like a trans structure would be. So this would be an E alkene. Any questions on this before I do just like a full nomenclature example? Okay. Let's take a look at so which factor do we base the priority on? It's the same priorities as you were doing when you were determining like R and S for a structure. So when you were doing R and S, like for this structure, for instance, you would say, because the fluorine is a larger atom, this would be our number one priority. We look at this carbon, it's bonded to a second carbon versus over here, it would say 2, 3. This is going clockwise, so this should be R. We're going to use those same priority groups down here. There's just only 2 options. We're either doing 1 or 2. Does that make sense? How about the right? Oh, yeah. Okay. So for on the right here, we have carbon. So these are both carbons. And then as we kind of branch out, this is carbon bonded to 2 oxygens because it's a double bond to an oxygen here. So oxygen is larger than these 2 CH3s down here. And that's why this top is our higher priority versus the bottom. We would think of it as carbon, oxygen, oxygen, carbon versus, oh, okay, cool. All right. So I'm going to do a fairly complex example. We're going to have a couple of different components to this, and then we'll get into some reactions. So let's take a look at this. We've got really 2 different possible directions we could go in. Either count left to right or right to left. To go to the longest chain, it would be 1, 2, 3, 4, 5, 6 here versus going the other direction. Taking a look at our substituents on this, we've got a BR at 2 and an alkene at 3 in the blue direction. I don't know why I chose that one first, so that would be 2 plus 3. In red, we've got our alkene starting on 3 and our BR starting at 5. So it makes more sense to go the blue direction. That's going to give us the lowest number of substituents. So we've got taking a, I'm going to draw these a little closer.
Where the double bond is, why isn't there a number?
I think I just drew it a little off. That fixed it?
Yes.
Okay. Oh, and I guess there was a substituent on 4 also. Okay, so on 2, we have a bromine. On 3, we have our alkene. Just gonna write alkene for this. We're 6 carbons, so this would be hexene. On 4, we have a methyl group. A couple of these have stereochemistry. So our bromine because it has a wedge there, it has a stereochemistry to it. So we can assign stereochemistry for this. BR our highest. Going left, right here. This is going clockwise. It should be R. Taking a look at our double bond. I can break this into two halves here. So we've got, I get rid of some of these numbers. Oops, I lost my R. Okay, for the top one, this ethyl side is going to be a higher priority than this methyl side. And then this side with the bromine is going to be a higher priority. The H here. Our two highest priorities are on opposite sides. So this would be an E alkene. If we put this all together, so we're going to start off by putting our stereochemistry within parentheses. Our bromine is on position 2, and we said it's R. So we would have a 2R. Our alkene starts in position 3. So that's going to be a 3E. And then we have our substituents, putting them in alphabetical order. 2-bromo. 4-methyl. And then for our triple bond, we're just going to indicate what position it's on. So 3, and then it's hexene. Should be all one word, I just kind of ran out of space. So looks like there are, nope, okay. Are there any questions about this before I move on from nomenclature?
Is there any difference between writing 3-hexene versus hex-3-ene, where you put
No.
the number?
You could write it as hex-3-ene. Sometimes if you get like when you start to get alcohols in there, which we'll talk about a little later, it becomes really confusing just to have all of these things at the end of it. But for the most part, there's no difference between writing this way versus this way. And I think tomorrow when we introduce triple bonds, when you have both a double and a triple bond, there is a way they want you to do it. But when you just have a double bond, it doesn't really matter which way you write it. Any other questions? Okay. We are going to move on to some reactions. So, first set of reactions I'm going to talk about are making an alkene. So, for making an alkene, we're basically just going to do eliminations. That should be pretty much all you guys know at this point. So, if we take some sort of haloalkane and we throw in a base, let's start with a small base. Which would be something like, let's go with like NaH, which is a very small base. Small bases are going to be selective for your less substituted position. So for doing an elimination, you're always going one carbon away from wherever your halogen is or your leaving group is. So if our leaving group is here, the positions that we care about are going to be 1 carbon away, so either here or here. So for this one, we have a secondary and a primary position. This is going to be selective for the secondary because it is a small base. It's going to pull off one of our protons. Kicking out this bromine, making a double bond, like so. Alternatively, if we use a large base, like this terp-butoxide here, this is so much larger that it's not going to be able to get into that secondary position. It's going to have to pull from the least substituted position. Kicking out this bromine here, giving us a different alkene. And this concept of large and small base is something you're going to see a lot throughout this semester. So it's a good thing to kind of have in the back of your mind. This will be a large base. But for right now, we're just going to be doing reactions with alkenes. So now that we know how to make one, let's talk about some reactions with them. So our simplest reaction with an alkene would really be to add an H2. So hydrogenation reactions, if you add an H2 with an alkene, it is essentially going to just reduce it down to an alkane. If we have multiple on there, H2 is a gas. This makes it infinitely hard to measure out the amount you have in there. So it's very difficult to actually get one equivalent of it to try to reduce just one of these double bonds. The reality is that you're always going to be in excess. That's not how you spell always. Also, I'm going to abbreviate excess as the letter X and S pretty much at all times. So if you see the letter XS, that just means you have an excess amount of it. So for this reaction here, we would reduce all of these down to just single bonds. Technically, this adds in a syn fashion, but because you pretty much always end up with at least one achiral center, it's not something I'm going to kind of focus on for this class, especially considering that this section is mostly a review. So H2 lets us reduce double bonds. We'll talk a little bit later about how if you had a carbonyl, you could reduce it down to an alcohol and things like that, but that's not for today. So let's start getting into some more complicated reactions. For instance, we are going to take this alkene here. If we add in something like HBr or HCl, what we'll have happen is we are going to pick up a proton. So our double bond, which has electrons on it, You'll notice that every time in this class that we're drawing arrows, we're always starting with a place that has electrons, going to somewhere that does not. So the double bond is made up of two electrons. It's going to come and attack this proton, kick out the electrons from this bond to our Br here. There are hypothetically two different possibilities that could happen. We could either make these two carbocations here. So this first one, we would have a primary carbocation. On this one on the right, we would have a secondary carbocation. Because we make a secondary carbocation on the one on the right, it is going to be dramatically more stable, and therefore this one is dramatically less likely to form. If you do have a situation like, for instance, I don't know, let's make it a chiral here. This, where you have secondaries on either side and add an HCl, you are able to actually generate both of these, and they both lead to product. But for right now, this example we're talking about currently, this is going to be the only option that's actually going to form. From here, get rid of this. We can have Br come in. It's negatively charged. It's going to want to attack at our positively charged center. And we can form a product. So this is kind of the simple form of the reaction. We are adding Br to the more substituted center. We add an H to the less substituted center here. When we have more complicated alkenes such as this one, we start to deal with rearrangements. So there's going to be two main types of rearrangements. There's going to be a hydride shifts and there's going to be methyl shifts. Our hydride shifts I'm going to talk about first. So as a review, there's three different types of hydrogens. Well, three different options for hydrogens in this class. You can either have H+, and this is what we refer to as a proton. It is literally a proton with no electrons. That's all it is. That's why we call it a proton. You can have hydrogen, which is where you have one proton and one electron. And we can have what we're going to deal with today, which is called hydride. It's also what we were using as a base earlier. And this is a proton with two electrons and a negative charge. This is called hydride. And it'll come up a couple times today. So when we're doing a hydride shift, like the one we're going to do on this molecule here, we're going to move both the hydrogen as well as the bond that's attached to it. The bond is made up of two electrons. That's where we're getting the hydrogen and the 2 electrons we need for a hydride shift. So let's get into it. If we had an HCl, I picked red there. Our double bond is going to pick up this proton. It's going to end up going to the less substituted center, so our positive charge goes to the more substituted center. We are going to have a situation where we have a carbocation. It's on a secondary position, and it's next to a more stable center. So there's a tertiary position here and a primary. We don't really care about the primary. That's less substitute. So our secondary center, our tertiary center, can do what's called a hydride shift, where we are going to ship these electrons over. That hydrogen or that proton and its 2 electrons are going to replace the secondary center, which is going to make a new gap on our tertiary center for a new positive charge. And we'll have shifted our stability from a secondary center to a tertiary center. So we went uphill in energy. We're now at a more stable center. If we look around, we're next to secondary, primary, primary. Our tertiary center is the most stable one. We don't need to do anything else. Cl can come in. Do an attack here. And we will now chlorinate at this position instead. So the whole reaction taking HCl, your final product is where you're chlorinating at this more substituted center. So hydride shifts tend to happen when you have secondary positions that are next to tertiary. Or the less likely situation is when you have primary next to secondary and primary next to tertiary. For the sake of these alkene reactions, this is the only one that can actually happen, but you'll see other rearrangements for things like SN1 or E1 where you can do these other 2 options here. But for what we're talking about today, it can be secondary next to tertiary. Our other type of rearrangement is when you have secondary next to quaternary. So for a methyl shift, we would need something like this here. Let's do this in water, do a slightly different reaction. So water and acid, still pick up this H+. Still make your carbocation. It is secondary. Its neighbors are primary and quaternary. Nobody cares about the primary one. So there is no longer a hydride to shift because these are all CH3s. We don't have any hydrides at this point. So all we can do is shift one of these methyl groups. From here, we look at our centers again. We have tertiary. Our neighbors are primary, primary, tertiary. There's nowhere that we can go that would be more stable. If we moved over to the other tertiary position, it would be equal energy. So there's no like anthropic reason to go there. So from this point, our water can come in. Not negative. Attack at our positive center. Because we're in water, we need one more step, which is going to be that another water is going to pull off this H. And make our alcohol. Okay, so those are some rearrangements. I'm going to talk through a couple more reactions, then we're going to take a break around 10 for about 5-10 minutes, and then we'll come back and talk through the rest of chapter 8. So, we talked a little bit about reactions in HBr HCl. When we add an HBr, it's going to end up adding the Br to our more substituted position, assuming we don't need to do a rearrangement. It's referred to as a Markovnikov addition. I'm just going to call it a Mark addition. Kind of abbreviate that a little bit. If we add in peroxide, this is going to push it to our less substituted position. So anytime you see peroxide, this should automatically indicate that you're going to be doing an anti-Mark addition, anti-Markovnikov. It'll be the same reaction you're normally doing with HBr here. It's just now going to add to your less substituted position. And on Wednesday, we're going to go over the mechanism for this. But for today, we're just not going to talk about it. So those are Markovnikov and anti-Markovnikov. Are there additions for HBr HCl, for forming alcohols? Take the same reaction here. We're going to have a little bit more complicated set of reagents. So if we add in H plus H2O, we can generate an alcohol. If we wanted, so this is our Markovnikov addition. If we want to do the anti-Markovnikov, where we add to our less substituted, we're going to add in, it's either indicated as BH3THF or just BH3, either one is fine. The Put the THF in parentheses here. You don't have it, I'll take either way. Followed by NaOH, which is our nucleophile. And again, peroxide. This is a mechanism I'm not going to go through in this class. It's a bit complicated. I just want you guys to know that if you see peroxide, you're going to be doing anti-Markovnikov. And adding your OH to your left substitute center. Okay, the last reaction we're going to talk about before we take a little break is going to be an alcohol addition where we avoid rearrangements. So, if we were to take this, I don't know, double bond here, add an H plus, H2O. As we talked about earlier, this one would end up doing a hydride shift. To make an alcohol like so. If we want to avoid this, we're going to use a different set of reagents. We're going to use mercury acetate. In water. Bad too. Followed by sodium borohydride. So NaBH4. This is going to let us generate this non-rearranged product. I think I'm going to take a break here. So let's meet back at 10:05. I'm just going to leave the Zoom up. I'm just going to turn off my camera for about, I don't know, 8 minutes. So let's take about an 8-minute break, and then we'll go through the rest of this chapter. So I will see you guys in a little bit. Are there any questions before we do that? There's not a recitation quiz today, but there will be one on Wednesday. And we get back, I can give you guys a little breakdown of the recies. Is there a reading schedule? I can give you guys a reading schedule. It's pretty much going to be a daily. We're pretty much going to cover a chapter a day. So today will be chapter 8. Tomorrow will be chapter 9. Chapter 10 will be Wednesday. 11 will be Thursday. 15 will be Friday. And then Monday we'll just kind of do a review. All right, so I'll meet back with you guys in about 6-7 minutes now, and we will get back to this. All right, let's get back to it. So let's kind of break down this reaction, and then we're going to talk through a couple more that go through similar pathways. So I'm on, right? Yeah, okay. We've got mercury acetate. So what this is going to do is we're going to have our double bond here attack the mercury acetate. It's going to kick out one of these OACs. We are going to temporarily make a transition state with a carbocation. These brackets mean transition state. And then this is going to close. So these electrons are going to go in, and we're going to make a 3-membered ring. The way that these 3-membered rings work is that typically your bond angle would be 109 degrees, but clearly this isn't. This is 60 degrees, which means these are really strained. And the way they alleviate strain is that they put the majority of that charge on the more substituted center. So they kind of do something that looks like this. Where they make a much weaker bond between your more substituted center, and they make a normal bond between your less substituted center. So we got a secondary and a primary here. Our primary bond's going to be normal. Our secondary one's going to be really long and weak. Because of that, when we add in water, it is going to selectively attack at this more substituted center, which is kind of what we expect. It'll kick out the electrons. That's a really bad A. From here, another water can pick off a proton. And then our last step is we're going to have sodium borohydride, which we're not going to talk too much about at this point. Later on in the class, we will. We're just going to refer to it as an H minus, as just hydride coming in, kicking off that Hg. To make our alcohol here. So it's a pretty complicated process. Something to note is that we make this kind of 3-membered ring here with a positive charge. The next 2 reactions we do are going to make the same 3-membered ring with a positive charge. They're just not going to have mercury there. They're going to have different things. So let's take a look at those. Got about 40 minutes left. Okay. And I've got maybe 5 reactions left to do. So up till now, we've done a lot of, everything's been a single addition. You've always ended up with adding one thing we care about as well as some sort of H here. We're going to move into some double addition reactions. The first one is going to be dibrominations. So for this, instead of adding an HBr, what we're going to add in is Br2. It's going to behave very similarly to HBr. Except essentially we're just going to substitute one of these Brs for an H. So up top here, we would attack this H. We'd end up kicking this bromine out. We'd make a positive charge. Our Br would come in, attack at this positive charge, and we go to our product. With Br2, almost an identical process. So our double bond is going to attack this Br, kick out the other one. We are going to brominate. This is going to close and make a 3-membered ring, just like we did with mercury acetate. And again, our positive is going to be mostly shared in that secondary center. From here, another Br can come in. And we are going to make a dibromination product. So we're adding 2 Brs now. If you want to compare these two reactions, they're very similar in terms of their product. The only difference is that we had an H over here. Now we have a second Br over here. This reaction is going to occur by an SN2 mechanism. So they're going to end up being anti to each other. If we have something that's a little bit more stereospecific. None of these are radical. They're just halogenations. The way you would know the difference between them is going to be your reagents. So if you're adding an HBr, you're going to do a single halogenation. If you're adding in Br2, you're going to do a double halogenation or a dihalogenation. Dibromination versus single bromination. So it's all about your reagents. So HBr is going to end up leading to single bromination versus Br2, end up leading to a dibromination. Yeah, I can draw that a little better. All right, so let's take a look at this molecule here. We're adding in Br2 again. Our double bond is going to attack. There are one or two possibilities we can have here. This can, it's what's going to cyclize either way. And when it cyclizes, it can either make this three-membered ring, or it can make this one. So either you're going to end up with both wedges or both dashes. If you think about like a triangle, it could be like this, or it could be down like this, but there's no way to make a triangle where one's going up and one's going down. So they both have to be the same. From here, when we add in our other BR, it's going to attack at the more substituted center, and it's going to do an SM2. So when this comes in and attacks here, it's going to flip the stereochemistry of that position. Which would give us, so this BR on the right here is going to retain its stereochemistry. The one that came in is going to end up getting flipped. And we're going to end up with an anti-configuration where our two BRs are going opposite directions. Same thing would happen on the bottom here. I'm going to draw it in green. So then this BR comes in and attacks. We are going to get the opposite occurred. So the VR that's on the right is going to have no difference to it. Still a dash. The spot where it attacked on the left is now going to turn into a wedge. You could simplify this by just drawing, when you're drawing your product, pick one of the two. They need to be anti. And then adding in plus minus. So this dibromination always acts in an anti fashion. In order to get to its final product. There's another reaction that is very similar to this. We're just going to change this last step, the nucleophile, from a bromine to an oxygen. Let's take a second to review this, though. So let's just keep using the same set of reagents. Adding in just HBr. We do a single bromination at this position. Adding in Br2. It's going to do a dibromination. Dibrominations are always anti. Our third reaction that we can do, I'm going to draw out the reaction, and then we'll talk through the mechanism. Is going to be if we take the same set of reagents or same starting material, add in Br2, and then water. what we're going to get is anti-addition of Br and OH. So if you wanted to compare these two reactions, you're going to be swapping out this more substituted Br for an OH here. The way this reaction occurs is going to be almost identical. So I'm going to walk through this bottom reaction. We are going to start with this starting material here, adding in Br2 and water. In our first step, we're going to attack this Br, form a temporary transition state. Which is going to close. I'm just going to draw one of the two enantiomers. To get to here. So at this point, if we're in water, so even if you're in an extremely concentrated, like 1 molar solution of Br2, water has such a high molarity to it that this would be 55 molar water. So there's 55 times the amount of waters as there would be bromine, and you're probably not even at 1 molar because it's a very high concentration. So it's infinitely more likely that at this point, instead of having another Br come in and attack, that your water is going to come in and attack. So it's still going to want to attack at the more substituted center because this Br bond is weaker there. It's going to do an SN2, which means it's going to flip the stereochemistry. We'll have another water pull off a proton. And give us anti-addition of Br and OH. Our OH ends up at our more substituted position. Our Br ends up at our less substituted position. So looking at this product here, the secondary position has this Br, tertiary position has the OH. Okay, we're gonna do some form some diols. So this was forming a bromination and an alcohol. Now we're just gonna form 2 alcohols. There's 2 different ways to do it. One of them is going to give us a syn product. One of us is going to give them the anti-product. So I'm going to take, let's do this molecule here. If we were to add an H plus, and water here, this would allow us to generate an alcohol. If we use a different set of reagents, so the first one is to be using what's called a peroxy acid. And essentially what that is a combination of a carboxylic acid and a peroxide. So a carboxylic acid would be here. Peroxide would be something like 2 oxygen bonds together. Peroxy acid can be a combination, so you're going to have your carbonyl. You're going to have an oxygen here, second oxygen, H. This is called a peroxy acid. The one that you will probably see the most is going to be MCPBA. And we'll talk about the structure of it later on, but you should know that MCPBA is a peroxy acid and it'll do this reaction. So I'm going to put an R here. I'm going to put MCPBA in parentheses. And then our second reagent is going to be just H3O plus or H plus H2O. And what this is going to end up giving us is anti-addition of alcohols. The last alcohol reaction is going to be the opposite. We're going to reuse a reagent called osmium tetraoxide. And a couple of different options to reduce this off. And what this is going to end up giving us, oh, she wants 3 plus minus. A little rough there. Is going to be a syn addition of alcohols. So our 3 different alcohol reactions, H plus H2O, gives us a single oxidation to an alcohol. This peroxy acid plus H3O plus will give us anti, not yellow. And then osmium tetraoxide and a reducing agent will give us syn. So let's talk about this anti-addition. If I take this peroxy acid, add it into an alkene here, what's going to end up happening is a lot of arrows are going to happen at once. I'm not going to make you guys memorize this one. Essentially, you're going to attack here, it's going to also attack. Yeah, this is a very complicated, weird web of arrows. And then you're going to end up with this 3-membered ring with an oxygen on it. This should look very familiar to something we've talked about earlier. This roughly looks like the 3-membered ring we made with the bromine, which should also look a little bit like the one we made with mercury. They're all kind of doing the same thing. They're all going to get attacked by an SN2 in order to create some sort of an anti-product. So this bromination one leads to anti-BRs. Technically, this bottom one also leads to anti, but one of them is a hydrogen, so it doesn't usually matter. But when we're here, our next step is going to be where we're going to pick up an H because we're adding an H3O plus. This is going to give us water. It's going to do an SN2. So we'll invert the stereochemistry of this top. Carbon, leave the other one the same. So this bottom OH remains. Or bottom, need the H there. We're going to end up with this protonated form, which can lose a proton. To give us anti-OH addition. So as we were discussing earlier, with a single H plus, and water, we're able to generate a single alcohol addition. When we have MCPBA, as well as H plus, H2O. This is going to let us generate a diol. They're going to add anti to each other. Our last possibility is going to be this osmium tetraoxide. Which is going to end up doing a syn addition. And I'm going to pull the book out and make sure what reagents they like to use. So that's what they use. Okay. We're going to use OSO4. And the book likes to use, what is it? NaHSO3. Followed by water for their last step. So we're not going to do a full mechanism for this osmium tetraoxide. I'm going to talk a little bit about it. Kind of the same thing we were talking about. We're going to do O's analysis. We're not going to go through a full mechanism for it. Well, that one we're going to go through much less. So the way this osmium tetraoxide works is it's a large linear molecule. It's not O5, it's OS. On your periodic table, it's, oh man, where's osmium? I don't even know. The transition metal. Yeah, it's element 76 is in your transition metal. It's under iron. But essentially this is planar. So when this kind of approaches, it's going to attack one oxygen. Another one's going to come in, and you're going to make a big complex. Where you're then able to reduce off these oxygens with sodium sulfate and water. And we're going to send product. So not covering a full mechanism for this one, just kind of talking through a little bit of it. This is roughly how it happens. Okay, I'm going to talk about two more things, and then we're going to call it for the day, just to kind of finish out this chapter. So this was a way to do syn and anti. Let's put it into something different. So if I was to use MCPBA, which was our peroxy acid, we would make anti-addition of alcohols here. If we do osmium tetraoxide, NaHSO3 H2O. This will let us do syn addition. For bromination, there's not a great way to control for dibromination, so BR2. The only way that you can actually generate a syn-like addition for one of these is you have to flip your stereochemistry on your ring, or not your ring, your alkene here. So if we want to make the syn equivalent of this, if we took instead of these trans bonds that we've been using, if we use a cis one, throwing in BR2, this will give us it'll give us a trans product, But if we rotate this to look the same, so we want it to just kind of match this configuration here, all we're going to do is rotate around this bond, configurational isomer. If I was to redraw this, it's a little rough. When we rotated 180 degrees, this was facing back. It's now going to be facing downward. And this lets us somewhat make a syn product out of these. It's not quite the same as having a reagent that actively does it. But if you switch your double bond, you can change the configuration of your structure. So that's another kind of important thing to think about, is that when you're drawing these out, you really want to try to keep whatever structure you started with in your product. So if I was to draw the anti or the normal product of this, I would want to draw it like this here. If I start rotating bonds, I'm going to end up with something different. So if I was to draw it like this here, this would actually be wrong. And the reason for that is that we've rotated along this bond here. So you flipped it 180 degrees. In order to make this correct, you'd also have to flip this position. And this would end up as a dash here. So anytime you're rotating things, bonds like this, if you flip it from down to up, it's going to flip dashes to wedges, and that's going to be an issue. So something to look out for. If you ever need to make a syn bromine addition, you probably have to do it through the opposite cis trans as your final structure. Okay, last reaction I'm going to talk about today for a little bit is ozonolysis. So an ozonolysis is going to be where we take a double bond here, throw in something like O3 and DMS. And what this is going to do is it's going to cleave our bond. Down the middle here. And we're going to end up oxidizing both ends of them. To carbonyls. Sometimes ketones, sometimes aldehydes. In this case, these are both aldehydes. This is a very long mechanism, and I'm not going to go through it. The way that a lot of people like to think of this is you're literally going to just kind of lengthen the bond here. So I'm going to draw a really long one. You erase the middle of it, draw an oxygen on both ends, you can get to your final product. If I have one that is in a ring, so for instance, get rid of this. This here, if I add an O3, When I cleave this, I've cleaved this bond here, but it's still attached to each other by the ring itself. So I could draw this as this here. We've separated that bond, made carbonyls on both ends, but the ring itself is still attached. Okay, let's do a bit of a review, and then I'll let you guys go for the day. So, reactions we've talked about. First one is adding in H2 and platinum. Going to reduce down to just a single bond. Adding in HBr or HCl will let us make haloalkanes. H plus H2O will give us a single alcohol. I'm going to write a note on this one that says can rearrange. If we want to avoid a rearrangement, we're going to add in mercury acetate. And water followed by sodium borohydride. We've got our dye additions. I'm going to use a different molecule for that, so let's kind of draw a line here. If we add in Br2, we can dibrominate. That R is a little rough there. Adding in our peroxy acid. Followed by H3O plus. Oh, I forgot Br2 and water. I'm going to do that one first. All right, let's do Br2 and water first. Keep them together makes more sense. So Br2, H2O. We're going to get an alcohol and our more substituted, Br and our less. Now we're going to do our peroxy acid. Let's just get anti-diols. We could add in our osmium tetraoxide. Which will get us to a syn diol. And then finally, ozonolysis. Let's just break apart this double bond into two carbonyls here. Okay, so that is all of chapter 8, or at least all of it that we're going to cover in this class. Tomorrow we will start on chapter 9. Chapter 9 has a lot of similar reactions. Apparently there's an issue on chapter 9 readings on Canvas. I'll fix those today. So I'll get that fixed before recitation starts. So just take a look at that in a few minutes. Okay, so chapter 9 tomorrow, it's gonna be a lot of the same reactions. We're just gonna do multiple things. There is no quiz today in recitation. For accessing the recitation, if you just go to the recitation Canvas page, there should only be one link on it, and that'll be the link for the recitation. Yes, I will post the recitation as well as the video from today's lecture. It'll be posted in the recitation Canvas, and this one will be posted in the regular class Canvas. So
Will it be posted today?
yes, I should get it posted today.
Okay, thank you.
You're welcome. All right, I will see you guys tomorrow or in recitation later today.
Thank you.
You're welcome.